Good morning, everyone. The third day of our faculty development program, hands-on approach for design and implementation of lab on breadboard, a blended learning, jointly organized by the Department of Electronics and Communication Engineering and Department of Electrical and Electronics Engineering, the National Institute of Engineering, Mysore. First two sessions, we have discussed about how to implement the basics of electronics in using the TINA software. Today, the third day, we will focus mainly on the power converters, the design and simulation of power converters for solar energy harvesting, basics of power converters, and how to simulate that one using TINA. And today's schedule is the morning sessions. We have design and simulation of power converters for solar energy harvesting, part 1. And later we'll go for the part 2 sessions, that is basics, and then more into the solar energy harvesting systems. In the afternoon sessions, we'll have the hands-on sessions. Today, we have our eminent speaker, Dr. Gurumurthy sir, Professor, Department of Electrical and Electronics Engineering, the National Institute of Engineering, Mysore. Dr. Gurumurthy sir has received his Bachelor of Engineering in Electronics and Communication Engineering in 1984 from the National Institute of Engineering, Mysore, MSc Engineering in Power Electronics from the Indian Institute of Science, Bangalore, and PhD on the topic Flywheel Energy Storage Systems from IIT Bombay. As a scientific officer in PARC, he has made contributions in the field of power electronics and works related to variable speed drives, power supplies, special purpose instruments, and control systems used in the nuclear facilities for 3.5 decades. He has carried out in the design, development, installation, commissioning, and maintenance of high-speed drives, UPS, and control panels for the process plants. Some of the important research contributions include design and development of high-speed drives for special purpose machines and BLDC machines. Also, power converters, special instruments required for high-speed rotor balancing, controller for BLDC generators, flywheel energy storage systems. Currently, he is working as a professor at the EEE Department of the National Institute of Engineering. He has published several research papers in international journals and conferences. And also, he has a patent in his own name. A warm welcome to you, sir. And also, I welcome all the participants for the day 3 session. Over to you, sir.
Thank you, Dr. Shankar, for the introduction. Okay, let me start my slide, share my slides. Yeah, very good morning to everybody. I hope I am audible.
Yes, sir, you are audible.
Yeah, okay. Yeah. So we are entering the third day of this program. In the first 2 days, you have learnt about the mainly the electronic circuits, how to design the circuits, how to model it and do the circuit simulation, see the responses and other things. Today we are going to discuss about the power circuits. Last 2 days you are concentrating on the electronic circuits. Today we are going to discuss about the power circuits. So what is the basic difference between these two? Okay. So if you know the difference between the electronics, electrical and power electronics, then we understand the difference. So from there, I think we can move on. Okay. So now basically, if you just in a simple words, if you make the difference between electronics, electrical power and power electronics. So then we will be able to see the difference, we can start understanding the power circuits. So basically, all circuits are same. All circuits follow Kirchhoff Ohm's law, Kirchhoff current voltage law, and Faraday's law of electromagnetic induction and things like that. All circuits follow the same laws, but the approach in the design, utility wise, it is different. So the way we look at the circuit is different. Okay. So now if you see the electronics, basically it deals with the analog digital signal processing.
Sir, you are not audible, sir. Gurumurthy, sir.
Just a minute.
I think on its own it is good. This is yeah, that I have done it.
Is it audible now?
Yes, sir.
It is audible. Okay, fine. Yeah. Yeah. I hope now I am audible.
Yes, sir.
Fine. Yeah. Okay, so the electronics discipline, it deals with the analog digital signal processing basically at low voltage power and computations, controls, then arithmetic logical operations on the signal. So basically we concentrate on the signal integrity and accuracy resolution and the response to various frequency components. These are the ways we look at the circuit in the electronics engineering. In the electrical power, basically deals with power generation, transmission, distribution. Mostly it is all high voltage and very high power. So what we do in power means we are dealing with the energy. In the electronics, we deal with the signals. This is the basic difference. So when we are dealing with the energy, so we have to look at the efficiency, power loss. They are all very important because energy is very precious. We cannot afford to lose energy. We have to save energy as much as possible. So power loss, these are the points we look at when we are dealing with the circuitry. And as we are handling the high voltage and high power, we have to see the human safety. And of course, there is a lot of energy is handled and there will be a lot of losses and all the thermal management. These are the things we look in the electrical power. Now the third part is the power electronics. What power electronic does? It is actually processing the energy. You see, energy is handled by the electrical power, the signal processing and other things in the electronics. So here actually we are doing the energy processing. Energy is available in different forms. Electrical energy, mostly we use electrical energy in the form of voltage, current, power control. So these things are done in the power electronics. So since we have to have the control over the voltage, current or power or in speed and things like that, we have to have the closed loop feedback system. So we have to sense the signals and process it and adjust the set and feedback and things like that. So we have to have the signal processing as well as the power handling together. So that's why in power electronics our main focus is on the power as well as the signals. So that is what is the basic difference. So we are going to discuss about the power circuit design and the simulation. The power converters for solar energy harvesting, that is the topic of today. Okay, so what we are going to cover, what is covered in this presentation. So now we are going to discuss about the power converters. So why power converter is required in this energy processing industry, and how the power converters work basic principle of working, and how to design the various components of the power converters and simulate it. Okay, then finally how to implement these power converters. So these are the basic things which are covered in this presentation. Okay, now okay, just okay. So we are going to discuss about the solar energy harvesting. So we have solar energy in the form of light. So energy is available in the form of light, which comes from the sun. So light is the source of energy, that is solar. Wind, the energy in the form of velocity of the wind. And tidal energy, that is the energy stored in the waves, tidal waves and things like that. Okay. So now, as the you cannot use this energy as it is. We have to convert it to the usable form. That is one part of it. So as the intensity of the light varies, the voltage also varies. Okay. So basically, we have to convert these energies, whether it is a velocity or the sunlight, to the form where you can easily transport from one place to other place and use it easily. So naturally, the electrical is the electrical energy is a form which we can easily use it and transport from one place to other place. So that's why it is the most prevalent form of energy which is available for the users. Okay. So now once we talk about electrical, so then voltage. So now the solar cells will convert the solar light in the form of voltage. So as the light intensity varies, the voltage also varies. In case of wind, so as the wind velocity varies, the voltage output also varies. Okay. But all our gadgets, electrical gadgets which is connected to the supply, all works with a constant voltage. For example, in our households, whether it is a light like incandescent lamp or LED lamps or the fan or a refrigerator, whatever gadgets we use in the house or in the industry, they are all designed to work in a constant voltage and constant frequency. Okay, so the supply frequency and the voltage should be constant. Now, if you see the solar energy source, when the intensity varies, the voltage varies. When the wind velocity varies, the voltage varies. So that is not, even though energy is available, you cannot use it because it varies. Our gadgets are fixed, designed for operating in the constant voltage. So that means there is a energy source is there, load is there, but they are not compatible. So the incompatibility between the source and load is there. To overcome this incompatibility between the source and load, we have to have some power converters. That is exactly what is power converter is about. These power converters will convert this variable voltage which comes out of the energy source to a constant voltage and constant frequency, which is to make it useful. Okay. Now, if you see the solar panel, solar energy, we are in this whole of our presentation, we are concentrating on the solar energy harvesting. So if you see a typical solar energy harvesting system, it looks like this. There is a PV array, photovoltaic array is there, which will convert the light intensity to current or the voltage if you connect a resistor. So it is a variable voltage source. So now the variable voltage source is given to the boost converter or any power converters, let us put it. Okay, so this power converter, what it does, the variable input voltage, it will convert into constant output voltage. Irrespective of the input voltage variation, the output voltage is constant. So then this, suppose you have AC load, then you have an inverter. If it is a DC load, straight away you can use this DC link to tap the power. So the inverter will convert from DC to AC. So these are the basically power converter or a DC to DC converter, or DC to AC converter, or AC to DC converter. So it will change from one voltage to other voltage. Like DC to DC converter means maybe low voltage DC to high voltage DC, or high voltage DC to low voltage DC, or fixed voltage DC to fixed voltage AC. These are the things. Okay. So this is the typical energy harvesting system from a solar. Now let us see what is expected from a energy harvesting system. You see, the energy source is available. We are going to harvest that using these power converters to the load. So naturally, what we expect, the harvested energy should be as high as possible, as much as possible. Suppose you are able to harvest all 100% energy which is stored, that is the best system. Okay, so these are the expected things from a energy harvesting system. Energy harvested should be as high as possible. Then the converting extracted energy to the electrical form, because electrical form you can use it easily, you can transmit it from one place to other place easily, and the efficiency of this source, that energy, this source is maximum, higher compared to other type of energy sources, so it has to be in the electrical form. So the third one is the whatever electrical, it has to be in the electrical form, the electrical energy in the form of the required voltage and frequency. Whatever voltage you want, whether you want 230 volt AC, 230 volt 50 hertz, or 110 volt 60 hertz, or 24 volt DC, 48 volt, whatever required, it has to be converted to the required form. That is what is the third expectation from the energy harvesting system. And this is what is expected from the energy harvesting system. So this is where the role of power electronics will come into picture. So power electronics consists of some power semiconductor switches, some filter and energy storage components, L and C, and which will make us to which will enable us to convert the energy to the form what we require. Suppose this is a typical power supply scheme. Let us assume there is a photovoltaic cell of 36 volt. So different sort of photovoltaic cells are available, different voltage levels. So just I took it for an example. So 36 volt is the nominal voltage. Okay. So it will, depending on the light intensity, it can go up or it can come down with from this nominal voltage. So the maximum, with the intensity is maximum light intensity. So then it can go up to 42 volts, or it can come down below 30 up to 30 volts. So the range of voltage variation is from 30 to 42 volts. So this is the output of the energy source, that is solar cell, which is available 30 to 42 volts. But what we want is different. We have wide requirements of the voltages. Like for example, you want to charge your cell phone, you need a 3.3 volt. Okay, you want to charge the battery in your house for the UPS, you need 24 volt. You have a laptop, you need 9 volt, or 230 volts 50 hertz for other gadgets, household gadgets, like this. The wide variation, different voltage levels we need, and there is a varied input voltage is there. So we need to have this block. This is what is the power converter is all about. This is what we are going to discuss in today's session. So power converter, it may be a buck converter, which will it is a DC to DC converter. From high voltage to low voltage, it will go convert, and a boost converter, it will change from low voltage to high voltage converter, and AC to DC. AC input, it can convert it to a DC output, or DC to AC. The DC input can be converted to AC output. So all these things are called as power converters. So we are going to discuss about this today. Okay, so since our focus is on solar energy harvesting, let us try to understand what is solar cell. So being electrical electronic engineers, we know what is diode. Okay, so diode can be forward biased or it can be reverse biased. Suppose if the diode is reverse biased, that is its anode is made negative and cathode is made positive, means the negative voltage is applied to the diode. So it is reverse bias. Reverse bias means it will offer high resistance and no current will flow, theoretical, ideal diode. But the real diode, there will be some leakage current which will be flowing. The leakage current which is flowing in the diode, that is because of the charge carriers which are thermally generated because of the temperature. So temperature, every 10-degree rise in temperature, the current reverse saturation current, this is called as reverse saturation current of the diode. Reverse current, saturation of the current doubles every 10-degree rise in temperature. So once you increase the temperature, current will increase. This is what happens. Now, instead of increasing the temperature, if you eliminate this junction with the light, light also is a form of energy, like from heat. So light, if you expose this junction to the light, then also the charge carriers will be generated. Okay, so these charge carriers, the number of charge carriers generated thus is proportional to the light intensity. Light intensity varies, the current also varies. This is the basic cell. So,
Participants, please mute
no,
yourself. Participants, please mute yourself. Sir, you can continue. Sorry for the interruption.
yeah, so it distracts. Yeah, this is the basic functioning of the diode, and this principle is used in the solar cells. Solar diodes are basically designed in this fashion so that the solar energy, light energy is converted to electrical energy. Okay, so that is the basic solar cell. Now the solar cell is there. There is a we have to devise the characteristic of the solar cell. Now let us see what is how it behaves. Okay. So basically, solar cell, we can understand the solar cell by understanding the current source. Suppose there is a constant current source. Okay, so it is represented like this, right? This all we have studied. Okay, so there is a constant current which is flowing. We are going to connect a one load resistor here like this. So current will flow like this. So what is the voltage developed here? So voltage developed equal to whatever the current which is flowing into resistance. Suppose if you plot this voltage versus this current. Now you see this is the characteristic of the resistor. Like if you increase the voltage, this is just Ohm's law. Okay. If you increase the current flowing in a resistor, voltage across the resistor will increase like this. Okay, like this, different resistors values. Suppose, okay, so I will just call it as R1, this is R2, and this is R3. So R1 is less than R2, less than R3. Okay. Now lower value resistor you connect R1. So that means the current is constant because it is a constant current source. So this much voltage is developed across the resistor. So this will become V1. So now you increase the resistor to R2, then the voltage drop will be V2. I am just writing the volt VO. Okay. Now you increase the resistance to R3, the voltage is V3, right? So that means as you keep on increasing the resistance value, the voltage will keep on increasing. So finally, theoretically, it will go to infinity if you open circuit it. So this is what is the ideal current source. This all we have studied. So now let us come back to the IV characteristic of the solar cell. Whatever you are seeing in the right side of the slide is the IV characteristic of the solar cell. Now you see the current, as I told you, the reverse saturation current of the diode. The current of the solar cell is proportional to the light intensity of light. Okay, so now lower intensity means I will call this as I1, I2, and I3. So at different intensities, the current will be different. So these three curves for different light intensities. Okay, so as the intensity increases, the current also increases. And since it is a constant current source, the voltage across it also changes. So let us try to understand this curve. As an ideal current source, the load resistor is infinity, then voltage induced is infinity. That is what is ideal case. But in the case of solar cell, it does not happen. It increases up to certain value. Afterwards, it starts decreasing. Like for some given intensity, I3, the current is this much, I3. Okay, so it keep on as you increase the load resistance. I'll just draw this load resistance curve. This is one resistor. Okay. Now I am writing R1, R2, and R3, similar to whatever earlier I have explained. So now let us take the intensity I3, light intensity I3. Okay. So you have connected a resistor R1. The voltage drop across the cell is V1. Now increase the resistance value to R2. Then voltage induced will be V2. Now increase the resistor to R3. So voltage induced will be V3. Like this, the voltage increases. Okay. Now this is the line which is parallel to the V is infinite resistance. So once you go, the infinite resistance means it is open, actually open circuit. Current source is there. So this resistor you are keeping it open. So open circuit. So open circuit, the voltage is this much. Okay, so that it does not go to infinity as an ideal current source. Correct? So that means this is a infinite resistance line. Similar way, this is R equal to 0 resistance line. So once the resistance is infinity, that means it is open circuit. This is the voltage which will get developed. So this is called as VOC, open circuit voltage. When you keep the solar cell open, this is the voltage you can measure. So this is the open circuit voltage. Now, if you short circuit the cell, then this is what is the current flows. So that is why this is called as short circuit current. So short circuit current and open circuit voltage. These are the main specification of the solar cell. Okay. So the voltage what you get out of solar cell is a function of the load what you are going to connect. That is what is happening. Okay. Now let us try to understand this. I hope this part is clear to everybody. Okay. So now, as I mentioned in the beginning, our focus is main energy and the output power. So we have to extract as much energy as possible. Okay. So power we have to get it from the cell. What is the power which is drawn from the solar cell? Power output equal to voltage output into current output. V into I. That is the power. So we are interested not only in voltage or only in current. We are interested in the power because voltage may be very high, but current if you are not able to draw, then there is no use. It is not useful. So we need the power. So that's why let us try to understand how much power we can draw from this source. As I have shown in the earlier slide, as the resistance is decreasing, you can say this is one resistance, okay, R1, and this is the another resistor, R2, okay. Now you see here, what is the power drawn by this resistor? This is your V1. So V1 equal to V1 into, almost I assume that this is a flat curve, it is constant. So V1 into ISC, let us say, you get. You go to R2, P2 equal to V2 into, the current has come down actually. So this is the, okay, I'll call it as IO. Okay. So now, in the first case, the voltage is less, but current is high. High current, low voltage. Power is something. In the second case, the voltage is very high, voltage is more, but the current is less, the power is less. So that means even if the resistor is low also, the power is less, high also, power drawn is less. So that means between these two, R1 and R2, there is a point where the power is more. So as you go on increasing the resistance, the power will increase. Okay, R1, R2, R3, like that. If you keep on, these are all constant resistance lines. Okay, so you keep on increasing the resistance, power will keep on increasing. So there is a knee point from where the current will start dropping down. Even though voltage is increasing, current is dropping down. So that is why there is a point where the current, the rate of fall of current is much higher than the rate of rise of voltage here. So that's why power again comes down. So that means there is a point where there is a power drawn is maximum. Okay. So that is the point where we have to operate. Okay. Now you see this curve. This is the IV characteristic. This is the curve. So there is a point. Now if you plot the power, so when you short circuit it, power is 0 because the voltage drop is 0, V into I. When you open circuit it, voltage is there, current is 0. Again power is 0. So in between there is a power is maximum. If you plot the power versus various resistances, so then you can see this curve. Okay, power varies like this. So that means how to find out this point? How to find out the point where the power drawn is maximum? So you differentiate the power. Power is varying with respect to the output voltage. So dP by dV you find out and you make it equal to 0. So then you will get the power is maximum. Power is maximum at when this dp by dv equal to 0. So that means in your computation you have to do this and find out the point where the power is maximum. You have to operate the cell, solar cell and the power converter at this point. So that's why we have to have a tracking system, power tracking system, how much power it is being drawn. So that is called as maximum power point tracking, MPPT. You must have heard in lot of advertisements this solar battery charger and all these things you must have seen. So they say that MPPT feature is there. So that means that maximum power point tracking system. Okay. So that's about the solar cell, what we have to do it. Okay. So now we know how the solar, what is the principle of working of the solar cell, how solar cell works, and what is the characteristic of the solar cell. Okay. Now we have to design a power converter to match, because this match this characteristic with the load characteristic to make the source compatible with the load. So what we need, we are basically thinking about a source voltage source. So we need a voltage controller. Okay. Then we need voltage controller is required because input voltage varies. As the intensity varies, output of the solar cell varies. So input to the converter varies. So that's why voltage controller is required. Next is power, maximum power point tracking system is required, because we have to extract as energy as maximum as possible, as high as possible. Next, we are going to get DC here in this system. So we need, suppose we have AC load, then we need a DC to AC converter. This is nothing but inverter. Okay. So these are the basic control system needed for the energy harvesting system. So now if you see a typical MPPT controller, typical energy harvesting system, if you see, it looks something like this. There is a PV array is there. This is actually the solar. So its output is there, which is variable. Suppose if you see, it may be like this, it may be varying like this, depending on the intensity. So this may be the DC bus voltage. Maybe say with time, means morning till evening when you pass, that intensity varies, the input voltage varies. So here, if you see, you have to have this block. This is what is our power converter. Okay. So by introducing this block, you are making it like this. This is T. This is VO. So this is actually VO. So this variable DC to fixed DC, we are converting with the boost converter. And one is that task. Second one is the MPPT, that is maximum power rated. It will adjust the voltage such that the power extracted is maximum. Okay. So here actually you may see here that the DC bus voltage and DC bus current are sensed into the control. This is actually the electronic controller. These are all electronics circuits are there. So it may be it is having some few current and voltage sensors. Then there is some feedback circuits and other things. then maybe some microcontroller and things like that. Like whatever yesterday and day before yesterday you have studied about the op-amps and signal processing circuitry. Those circuits will be there, maybe some with microcontroller and software embedded into it, and finally it will generate the pulses to the boost converter. So finally it will get the required output voltage. So now a boost converter looks something like this. So there is this is the configuration. Okay. So there is a solar cell, PV panel is there, photovoltaic panel is there. So straight away it is actually basically like a current source with the IV characteristic whatever we have discussed, and its output of this solar panel is connected to a boost converter. Boost converter consists of an inductor, and there is a semiconductor switch, another diode is there, and a capacitor. So this is what is the output voltage you are going to get from this converter. Solar cell, power converter, and here you are going to get a DC voltage. So if you have, this is DC voltage. So if you have AC loads, then you can have an inverter to convert DC to AC. Or you can, if you want to feed back this energy to the grid, so then you can connect these points to the AC grid. Okay, so the loads are located somewhere else. Okay, so now let us see how these things works. Now we have understood that there is a converter required to make the source compatible to the load. Okay, and let us try to understand boost converter, how it will be useful. So now you can see here, this is the boost converter circuit. You have one inductor and there is a switch and capacitor. This is simple boost converter. Okay, so this is what is the output, this is the input. So this is the circuit diagram which is shown here. This is the inductor. Now let us try to understand how it works. There is a switch which is a MOSFET which is having.
ഇന്നത്തെ കണ്ടോ ശങ്കർ സ്ലൈഡ്സ് ഒക്കെ റെഡിയാക്കി വെച്ചിട്ടുണ്ട്, അവരുടെ ഇൻട്രൊഡക്ഷൻ്റെ ഇതെല്ലാം ചെയ്തിട്ട് ഞാൻ.
Please mute yourself, participants. Please mute yourself.
Yeah.
So you can continue. Sorry.
Yeah. Okay. Yeah, there is here the semiconductor switch used is a MOSFET. Okay. So MOSFET means metal oxide semiconductor field effect transistor. Okay, it is having drain, source, and gate. So gate you are going to give the control pulses, and drain and source you are drawing the power. Let us try to understand how it works. So in the gate we are going to give a pulse like this. Okay, voltage pulses. This is called as control pulses. Okay. So this is given to the gate. So this is the 0 volt and here it is 15 volt. Okay. So once you give this waveform to the gate, what happens? When you make the gate 15 volt, the switch will become on. Okay. So once you make the gate voltage 0, then switch will become off. So that means you are making the switch on and off by using this train of pulses, this square pulses. Okay, let us say what will happen. So once the switch is on, you can see the equivalent circuit. If you see, there is a inductor here, and the switch is short circuited, and the current will flow. So what will happen? This is the source. Source means it may be, I'll just show it as a battery. Okay, with this is positive and this is negative, Vs. The current will flow through the inductor, through the MOSFET and back to the source. This is what is the current flow direction. This is the current which flows in the inductor. Okay. So now when you make the switch off, okay, what happens? This switch will, MOSFET will go off. Okay. The current, the property of the inductor is such that it will not allow the current to fall instantaneously, but the device current will fall instantaneously. Now, if you see here, the device current, let us say this is actually ID. I'll call it as ID. This is ID. So the device current will rise like this in the inductor. Okay. So device will not allow the current to flow in it. So that means it becomes 0. This is I maximum and it will become 0. This is the ID. Okay. So now the property of the inductor is such that it will not allow the instantaneous change in the current. It will try to maintain the current. So earlier the polarity of the inductor is like this. Okay. Now it will change the polarity such that the current direction is remaining same. Current will not change through it. So the diode will start conducting now. The diode will become forward bias, and the same current will try to flow through the diode, all through the capacitor, and again back to the source like this. So in this process, what happens? The capacitor will get charged like this. So once the capacitor charge is increasing, current in the inductor will start decreasing. So now if you see the current in the inductor, this is IL. I just call this as IL. So what will happen here? So current will rise when it is on, device is on. So current will fall when device is off. Okay. Next, again the second next pulse will come. Again it will rise, and again it will fall. So like this it continues. So this is actually I maximum, and this is I minimum in the inductor. Okay. So this is called as current ripple, that is delta I. Okay. So these are the equivalent circuits when it is on and the device is off. This is the equivalent circuit. Okay. So let us now this you have understood. Now let us see the transfer function. Okay. Now just whatever I have discussed here, that is shown here. This is the inductor current. This is the device current. This is the current in the capacitor, and this is the voltage ripple. Okay. So now let us see the transfer function. So basically we are interested why we are discussing all these things, because we want to build a boost converter. This is the boost converter topology. So the output voltage is more than the input voltage. So we are trying to establish that relationship, how it happens. Now when the current is flowing in the inductor, when the switch is closed, okay, this is the voltage which is applied, that is Vs. Okay, when switch is closed, Vs, like if you write the equation, this is the L, actually this is the current. So L into di by dt. Okay. Now if you see the steady state, so di, what is di? This is di actually, from here to here. From here it starts rising through this thing, it will go up to maximum and comes down like this. Okay. So this is what is the di. So now if you see L into di by dt, let us say this okay, it is on for a duration t1 and off for the duration t2. and this total time I will call it as capital T. Okay, so capital T is the period which is equal to T1 plus T2. Okay, so T1 is on duration of the MOSFET. T2 is the off duration. Okay, so now let us say when it is this device is on delta I by T1 equal to Vs. This is one equation. Okay, when the device is off, what happens? The inductor current will remain same, inductor will be there, and the Vs voltage source is same, and this device will become open circuit, and there is a diode, there is a capacitor connected, and this we know this is the output voltage, this is the input voltage, Vs. Okay, now same thing if you apply the Kirchhoff voltage law, the voltage drop across the inductor equal to Vs minus Vo equal to L into di by dt. dt is T2 here actually. You see here, this is the second part. This is the first equation. This is the second equation. Current is dropping down. Okay. So T2. So now this is the second equation. When it is device is on and the device is off. These are the two equations. Now the delta I is same in a steady state. Delta I is same. The whatever amount the current rises, the same amount current falls. So here both these two are same. Now you substitute this delta I into this equation, then you will get a transfer function something like this. So you can find out T1, you can find out T2. So then this is the delta I you are going to get. Okay. So now if you simplify these things, substitute these things, so you can get Vo equal to Vs divided by 1 minus K. So K is T1 divided by capital T. So this is called as duty cycle. K is called as duty cycle, that is given by T1 by T. Okay. So now you see here, T1 is always less than T. The maximum value of T1 can be T. That's all. So always this K is it varies from 0 to 1. This is the maximum value of K and this is the minimum value of K. So now if you see this equation, Vo is always higher than, always more than Vi. Correct? Because K can have a minimum value 0, that is Vin, maximum value 1. So then this equation goes to infinity. So that's why it is called as boost converter. So it can be used for boosting the voltage. Okay, I hope that part is clear. So now basically since we are designing this power circuits, we should know design of power circuit means those circuits, the component should be able to withstand the voltages, and component should be able to carry the currents what is drawn by the load. Finally the load power what is going to the load from solar panel, it will flow through this converter. So that's why you need to calculate this current and voltage values. So that's why these calculations are important. So now in the same philosophy you apply the Kirchhoff voltage law, current law, and you can find out the value for delta I and delta Vc. That is what is current and voltage ripple. Like suppose if it is load current is something like this, average current. So this switching may go like this. Okay, so this is I maximum and this is I minimum in the inductor, and this is the I naught. So I'll just show you what are these things. This is that inductor, then there is a diode, then there is a switch and capacitor and the load. Okay, so this is the load. So this is what is I naught. This is what is that IL. Okay, this is what is IL. IL is flowing through the inductor. Okay. So now these are the ripple voltages. By applying the simple rule, you can find out the ripple voltage and ripple current. These are the things required for finding out the rating of the components. Okay, so from solar cell, this is the solar cell. It goes to a power converter. Then finally it goes to the load. Okay, so all these power converter components has to carry these currents, whatever currents we are discussing, current and voltages, that will flow through the power component. That's why this calculation is very important. Okay, fine. So now let us say we have to design a power converter. That is what is we are looking for. Okay, so what is meant by design of a converter? So you have to build a converter which has only 2-3 components. What is that? One is the inductor, then other is the switch, in another diode, capacitor. So that's all. This is what is boost converter is all about. So this L, this C, there is a diode and there is a transistor. Okay, so you have to select this component. This is what is meant by design. So that means you have to select this value of the components and rating of the components and the switching frequency. So this is in our hand. You have to decide. You have to give a pulses. So you have to select the switching frequency, capacitor and inductor. And the power device. Power device also a lot of different varieties of power devices are available. Maybe 100 volt 10 ampere, 600 volt 20 ampere, 1000 volt 5 ampere. Like that, varieties of devices are available. Which device you have to select? That you have to decide. That is what is actually design of a converter. Design is these things. Selecting these devices, capacitor, semiconductor device, voltage ratings, current ratings, what is the loss taking place in the device, how much loss it can tolerate, and the response time. Like these are all non-ideal devices. Ideal devices, it instantaneously it will get on. So it is called as turn on time and turn off time. Okay. So ideal device turn on time, turn off are 0. But here it is having some limited. It has some values. Okay. So that that's selection. So the switching frequency and this response time, like turn on time should match. Okay. So that is the second part of the selection of the components. So third part is specification of the assemblies. Finally, what we are going to do? Finally, this converter is nothing but a power supply. Like for example, you have a laptop, you want a power supply of 9 volt from a solar cell you want to take. So you have to convert, you have to build a converter which will take that whatever voltage coming out of the solar cell, convert into 9 volt source, and which you are going to connect to your laptop. So that means it is a DC power supply. Basically, it is a DC power supply. So that means the specification has to be defined. So what is the specification? Output power. So output power may be 100 watts, 500 watts, or maybe 5 watts, like this. So output power has to be specified. Second one is that output voltage. What voltage your gadget is working? It may be 9 volts, or it may be 24 volt battery, or it may be 3.3 volt for the cell phone, whatever it is. So then the input voltage. Input voltage comes from your solar cell. So solar cell you can have 12 volt cell or 36 volt cell, 18 volt cell, like that. Different voltages are there, and of course this is the range. As I told you, if it is a 18 volt is the nominal, so this may vary from 14 to 22. This is the range. If 36 means it will vary from 30 to 42 volts. So like this. This is the range of the voltage. That's why it is called as input voltage range. Then the regulations, when you load or when input or voltage varies, how much output voltage variation is there? These are other things. Then ripple factor and the protections like EMI, EMC and things like that. Okay. So this is the specification, how compact it is. Like you need a charger, it should not be too big. Like you have a laptop charger, it should not be, the weight should not be more than maybe 100, 200 grams. If it is some 2 kg weight, nobody will buy the power supply, right? So it has to be, and the size also should not be too much big. You should be able to keep in your bag, right? So that's why the size of the product size and portability, then the efficiency, all those things are important. So here I think I have not written the efficiency. So these are the specification of the power supply. Depending on the specification of the power supply and the requirement, we are going to design the power supply. Design the components of the boost converter. So now we know that the ripple in the inductor is given by this equation. This is the ripple in the inductor and ripple voltage across the capacitor. So now you see the ripple current is depending on the frequency as inductor value, supply voltage and K. So you have to balance all these things. Engineering is always a trade-off. You have to make a trade-off between trade-offs you have to make. Like you, for example, you want to make the power supply very compact, lightweight. So inductor L is going to add weight, okay, weight as well as cost, okay. So you want to reduce the size of the inductor, okay. Reduce the size. If you want to reduce the size of the inductor, because you see in this equation, this is in the denominator. If you want to reduce the size of the inductor, you have to have a smaller inductor value. But the delta I is same. So to have this delta I, then you have to increase the frequency. So that means if you want to reduce the inductor size, means that you have to increase the switching frequency. Okay. Same way here, you want to reduce the size of the capacitor, means you have to increase the switching frequency. Okay, fine. Let us, you may say that, okay, let us increase the frequency. What happens? Instead of 10 kilohertz, you operate at 100 kilohertz. How does it matter? The size of the capacitor inductor will come down. Size will become compact, size will become small, then it will become lightweight, everything, all the advantages. No, it is not that way. You increase the switching frequency, there is some other side effects are there. Your loss in the device is going to increase. So efficiency will reduce. So switching frequency, if you are increasing, what will happen? Your efficiency will come down. Efficiency reduces. Losses will increase. So you have to see the trade, you have to make the trade-off between these two things. You have to select a optimum frequency, optimum value of LNC. This is what is actually the design. Design is a skill. Each person will have different skills to select the particular things. Okay, so you have to do somewhere else, tuning somewhere else. So this is what is about the design of the boost converter. Okay, so now let us say we have selected the L and C, when we have selected the device and other things. Okay, now let us say we have to build a power supply. How to make a power supply? So we want a constant output voltage, right? As from the beginning we are discussing that voltage should be, all our gadgets are working with constant voltage. So you have to have a constant output voltage. So if the output you have to maintain constant means you have to have a feedback system. You have to address something, you see same thing is happening, and you have to have a closed loop feedback system. Then only it is going to work. So once you have a closed loop feedback system, that means it will take the feedback and it will compare the set. Okay, so that means how it looks like. Now we are the operator. Suppose it is a voltage controller, let us say. So we have a set voltage. Set voltage means maybe 9 volt, 24 volt, 36 volt, or 120, whatever you need. So set you are going to have. Okay. So then you have to compare whatever set is attained or not. So that means you have to have a feedback. Okay. Set and feedback. So this always this output is set minus feedback. So that means that is what we are going to get as the error. Okay. So this error is there. Then you can scale this error with some amplifier, like whatever yesterday and day before yesterday we were discussing about the operation amplifier and those things you can use it for scaling up. It means error may be some millivolt or something like that. You want to shift it to make it 0 to 5 volt from 0 to 100 millivolts. So you have to have some amplifier. Okay. So once you have the amplifier, then you have to have a controller. So to match the load, time constant, and the controller may be working very fast, load may be working very slow. You cannot, if you have to match these two things, then you have to have a controller with, we can say generally we use PI controller, proportional integral controller. So they have their own advantages and disadvantages. Like proportional controller have very fast response, and steady state error is non-zero. Always error is required for it to work. And the integral controller, if you see, the steady state error is 0, but the initial overshoot is more. The response is slow. So then again, it is a trade-off. You have to make the trade-off between all these things. So we have a proportional integral controller. Now you see in our boost converter, what is the input for the boost converter? It is just a pulses. Pulses we are going to give, and we are getting the output voltage. So here actually what you get is control voltage, that is VC. It is an analog voltage. Okay, but what we need for the controller is, boost converter is a pulse. So that's why you need to have another block which will convert this voltage into pulses. So then what you get here is pulses. Here it is voltage. Okay. So this pulse you are going to give it to our boost converter. So what is the block of the boost converter? Boost converter is having one input, that is V in. Another is the pulse input, and the transfer function is 1 divided by 1 minus K. So pulse, what is the pulse specification? Is the duty cycle and the frequency. So 1 divided by 1 minus k into V in, it will do whatever V in you are going to have. V in to this. So this is the boost converter. So the boost converter output is VO. Okay, so V in it will take, it will modulate with this PWM. So then V in into, this is actually multiplier block, V in into 1 divided by 1 minus k. That is the property of the boost converter that just now we have discussed. So this is what is the scale multiply with A. It is a scaling factor. Maybe I will call it as 1 by A. This is basically an alternator. So this is what we have to do. This is what is our closed loop controller. So if you have to build a boost converter, you have to make this block. So now your system is ready. You have understood what is solar cell. You have understood what is boost converter. You have understood what are the requirements, how to select the values of CL and switching frequency, etc. Now we have made a block diagram of controller, what you need to build. You see here, now you want to build practically. Now you are thorough with the design. You are ready with what you are very. You see here, I will just write it as A, B, C, D, E. Okay. So A is what? Actually, it is computing the error. So one error amplifier is required. Error computation and amplifier. So B is also A and B both are same. Their amplifiers are required. Then there is a PI controller is there, that is C. So you need here again, that is also an amplifier only, maybe one operational amplifier which you can build. We can build a PI controller. Okay. So another operation amplifier is required here. Then you see the D. D is what? There is a PW. So that means input is analog voltage. You want output as a pulses, which is proportional to the control voltage. Means pulse width should be proportional to the input voltage. So that means one PWM IC, which PWM IC which will convert the analog voltage to the pulses. Next is E. E is boost converter, that is L, C, then transistor and diode. These devices. These are all power devices. So then you have to sense this output voltage. Okay. So you need to have, okay, I'll call it as F. So you need to have sensors. If it is a current controller, it is a current sensor. Otherwise, if it is a voltage controller, it is a voltage sensor. That is what is required. Okay. Now these are the things you need to build this power converter. So you see that power devices. You can select a MOSFET or an IGBT or BJT, whatever you want, you are comfortable, you can select. You should be able to switch it on and off at a frequency which we intended to do it. Then the inductor for the power supply, inductor capacitor. Then the sensor to measure the voltage and current. So sensor means it is not very great thing. Like suppose you are using a small voltage. Suppose if your DC bus voltage is 24 volts. So what is the voltage? Simplest voltage sensor? Just resistor. So this you can take it as a voltage feedback. Suppose 24 volt is there. You need 2.4 volt. So you have R1 and R2. So you select R2 divided by R1 plus R2 equal to 0.1. So then your V fed back, suppose this is your equal to 0.1 into 24 volt. So that means you will get 2.4 volts. So this is what is the sensors we are talking about. Suppose you want to sense the current. So just have one small resistor which may be 0.01 ohm. So it does not affect your output performance. So then you take this as a current feedback. So this is what is the current and voltage sensor about. Then amplifier, maybe some, this is actually resistors. Amplifiers, you can have some LM324. There are several ICs are available. So then PI controller and pulse width modulator. Now you can have like a 555 timer. These are all very simple and most popular ICs. Then the power source, maybe whatever power supply source, you can have some voltage power supply. Okay, so these are the things, components are required to build the power converter. Okay. Okay, now we have to build the power converter. So these are the components required. Now we have to understand how these things work. Okay, you select some components and you try to understand how it works and put it in the circuit and build the system. Okay, just these are the things I have just selected. You can use any op amps, you can use any timer, any other components. Just I have selected these things for this FDB program. We have built some circuits using these components, simple components, so that to get familiarized with the concepts. Okay, these are the things we have selected. So now selection of the switch. Now we have decided that we need a semiconductor switch. You can select one of these switches, BJT, IGBT or MOSFETs. Then you have to select the ratings of the current and voltage ratings. Okay, switching frequency. Then these are the things. Then the efficiency, depending on what high efficiency you need for the power supply, you have to select the loss, how much loss is taking place in the components, in the inductor, or in the power device. All those things we have to select. Okay. Then the cost. Again, finally, when you are making a product, it should be cost effective. Otherwise, nobody is going to buy. Okay. The cost should be as low as possible, and the component should be easily available. Such component you have to select. Okay. So this is a product development. This is the approach you have to adopt for making a good product. Okay. Now I'll just tell you how to select these components. Okay. Means these are the aspects you have to consider while selecting the product. Okay. So I'll just tell you how to select the components. Now we have to select inductor, then a MOSFET, let us say. So this is the current ID. So you just recall whatever we have discussed in the earlier slide. The current in the inductor is IL, this is IL. So current in the inductor goes like this. Right? You just recall whatever we have discussed in the earlier part of this presentation. Okay. So this is your I minimum. This is the I maximum, and this is what is the IO. Okay. So this is the capacitor, and this is the load resistor RL, and this is what is IO. What we are discussing is IL. Okay. So now if you see the current in the inductor and the device. Now we have to select this device. This T1 is the device, let us say we have to select. So selecting means what? What is the current rating and voltage rating you have to select. Okay. So now you see here, this is the period at which the device is on. This is the period at which it is off. So actually it goes like this. The current in the device, sorry, it goes like this. So this is actually the average current, this is actually peak current. So that means what is the maximum current which flows is actually I max. Okay, so that means ID means the device should be able to take this current, that is I naught plus delta I. Delta I is the ripple, that also we have calculated. This should be the current rating of the MOSFET. Okay, this is current rating. Of course, you have to do some derating and all. This is actually theoretically this much you can compute. Maybe sometime the surge current and all we have to take into considerations. Then next is voltage across DS, VDS, drain and source. If you see here, when the device is on, the voltage across the device is 0. Okay. When the device is off, this is the diode will be conducting. So that means this is off. So whatever output voltage you are going to see, that that voltage is this device is going to see. So VDS is nothing but V output. It is a boost converter. The output voltage is higher than the input voltage. Suppose you are boosting by 5. Suppose 24 volt is your input. Suppose 24 volt is your input. Your gain is 5. Output is 120 volts, right? VO is 20 volts. So this should be able to withstand this voltage because the diode will be conducting. So VDS is this way. Then third one is switching frequency. Okay, switching frequency you are deciding maybe some 10 kilohertz, let us say. Switching frequency is your 10 kilohertz means it will become 100 microsecond period. So 10% duty cycle if you are taking, it will become 10 microsecond. 10 microsecond is your T1 or on time. Okay. So 10 microseconds should be far higher than the switching time of the devices. So suppose if switching frequency is 10 kilohertz, if you select your what you call on time and off time of the device should be far less than this. It should be less than maybe 500 nanosecond. Okay, so these are the way you have to select the devices. Okay, so then let us see the data sheets. You can see this is the data sheet of the MOSFET IRF 150. Are you able to read these figures? You can see here off state, on state current. So at 25 degree centigrade temperature, and this is at 100 degree centigrade. Okay, so at 25 degree the ID is 42 ampere. At 100 degree the ID is 30 ampere, right? Oh, 10 minutes. 10 minutes. Okay, you have to select the device based on these considerations. So this is about the current rating. Then the voltage rating is there, VDS, off state voltage and things like that. Then all these details are there actually. You can see this is the test conditions of 100 volt. Then you can see this frequency you have to decide based on this thing. This is actually rise time, fall time. So 11 nanosecond, then 45 nanosecond. All these things are there. So these are the things you have to look into the device specification while selecting the device. Okay. Next is that once you select the device, then you go for the IC. This is a timer IC. So that I have selected as a pulse width modulator. You need a pulse width modulator for our project. So this can be used for pulse generation and pulse width modulation. You can see these things. So you have to select the particular IC. You can select any IC. I have selected 555. Okay. Then you can see what are the pin configurations are there, which you have to connect where and things like that. What are the voltage current levels, all those things are there. So what is the power supply you can give, all those things will be available in this data sheets. Okay, let us go to the capacitor. Now the capacitor you have to select. Okay, so capacitors having the specifications, different specifications are there, like capacitor voltage rating and ripple current handling capacity, then the capacitance value. So like this, capacitance value you can select whatever you want. Then you can observe these things. You want to design a equipment which has to last for 10 years or 5 years or 15 years. You have to look at these specifications. See, for example, you see here, if you use the capacitor at 40 degree, then it can, the life is 1,25,000 hours. So 1,25,000 hours you can continuously operate. This is what is the meaning. So this divided by 24 hours into 365 days. Okay. So this is actually the life of the equipment. Finally, if the capacitor fails, your equipment fails. So this life in years. This many years you can use it. So you select the capacitor. One is the capacitor value you would have designed. So you have to select, like suppose you are operating at 100, so 10 kilohertz. So if you are selecting 10 kilohertz, you are selecting this ampere. So then you have to see that the current rating is this much. You see that current rating will not exceed this value. Okay, then IGBTs are useful at lower frequency and high power. MOSFETs are useful at high frequency and lower powers. And these are the things. Because of lack of time, I am skipping these slides. Okay, then I'll tell you the applications of the solar power. So solar power you can use in wide varieties of applications. Many places, in particularly this agricultural and all remote places where the power is not available, you need to protect your fields. Maybe you can use the power fence. Power fence means actually this high voltage pulses, high voltage pulses, and at a low frequency. It is injected into the fence lines so that it is a deterrent. Then water pumps you can use in the field and all. You don't have to draw the power lines. So in the daytime when sunshine is there, you can have a submersible water pumps powered by the solar. You can have one solar panel, boost converter, and a drive, maybe BLDC or any motor drives. Some security systems for remote places. You want to fix some CCTV cameras, etc. Then traffic lights where you don't have to draw the power. So okay, these are the different applications. There are wide varieties of applications. You don't have to, means some places it is very handy. Okay, we have come to the end of this presentation. So we have made some converters by using these ICs. Whatever ICs we have discussed, a 555 timer. This is actually a 555 timer is used. This is an error amplifier. LM324 is used here. And there is a battery is used as a source. This is actually the boost converter where the MOSFET is used and capacitor and this thing. So this is basically it is looking a very simple circuit, but it works very nicely. It is a boost converter which will boost 15 volt to whatever voltage you want. 15 volt to 30, 40, 50, 100 volts also you can have. And this is actually feedback circuit, voltage feedback. These are the ICs used. Maybe this in the afternoon when during the hands-on you can see the response by using Tina TI software. This circuit is simulated. It is simulated and it is working very nicely. And once you see all the things, then you can go for the building the boost converter circuit. Okay. So next is PWM generation, like pulse width modulation. So as the control voltage you change, width of the pulses also is changed. That is demonstrated by using the same 555 IC is used. And this waveform also you can see by running the T9 TI. And this is actually a power spin circuit. That it is actually powered by a AC source. Here also you will get a output high voltage pulses, maybe some 5 kV or 10 kV at an interval of 1 second. Like this is VO versus T. So this is a power fin circuit which is built. This is also there available in your hands-on session. You can just run it and see, have a feel of it. Then you can use the solar, this converter as the battery charging circuit. So this is the battery which is required to be charged. Required to be charged. So these are the circuits are available. Maybe in the afternoon session we can have the hands-on experience of all these things. Okay. Okay, I think that ends my presentation.
Dear participants, if you have any queries, you can unmute and you can ask the same. Dear participants, if you have any queries, please unmute and ask the same.
So no questions.
Sir, like I think
Yeah.
there is no questions. They have said thanks for such an informative and interactive sessions on converters. Another WhatsApp group is there. Few
Okay.
participants have messaged there.
Yeah. Okay, sir.
So
Yeah.
now, like we mark the end of session 1 of day
Yes.
3.
Yeah.
Thank you, sir, for giving such a detailed overview about the design of converters. We feel like we are sitting in the classroom and listening to the talk. It was wonderful. On
Okay.
behalf of the organizing team, I thank you.
Okay, sir.
Once again, thank you from our side. Next sessions, we'll start at 11:55.